Surprise, surprise, learn and adapt. Presented by myself, Dylan Walton, on behalf of my team, which also includes Nelly Bencomo and Huma Samin. Now, we have something called a self-adaptive system. These are a type of automated computer system that will make decisions during runtime. Self-adaptive systems typically rely on some assumptions made during their design. These assumptions are intended to help them handle scenarios they may find themselves in while operating independently. These assumptions that we make, though, may not hold up. The environment may constantly change, or our assumptions may simply be wrong and inappropriate, leading to eventual performance degradation. Now, sadly, these design time assumptions, though imperfect, are the best ways to produce self-adaptive systems. Surprise! A surprise measures the gap between an expectation and an observation, more of an assumption and the reality. These can include things such as something weird happening in a slideshow, or can be calculated mathematically using a quantified belief, which is what we will do in our work. We can adjust our assumptions based on the surprise to learn the impacts of our actions during runtime for our self-adaptive system. Surprise can then be used by our self-adaptive system to change its assumptions after the design phase without additional human interference. And I'm just noting here that there are different types of surprise, and we do look at two others, but we will mostly focus on confidence-corrected surprise for our work. So our approach was as follows. We model our environment using a partially observable Markov decision process, or POMDP for short. We produce a set of beliefs as to which state we should enter given our current state in action. When this belief is violated, we get a surprise. The goal now is to minimize the surprise in order to produce consistent results that are well adapted for their environment. We use the surprise minimization learning algorithm, the SMILE algorithm, which will reduce the surprise as run goes on. So here's just a generic outline for what happens. We initialize our beliefs. Based on these beliefs, we'll take an action. We will get an observation after the action is taken, and then we can calculate the surprise based on the difference between our belief and the observation. And using the surprise, we can then update our beliefs again to try and minimize the surprise going forward. And this process will repeat itself as many times as is necessary until the self-adaptive system is finished. We apply this to an RDM simulator example. A remote data mirror, RDM, is a type of online backup tool that maintains links to mirrors of a system/data. An RDM maintains several quality attributes, things that are not necessary for the functionality of the RDM, but we would like to have. There are three that we are concerned with. The maximization of reliability, which is simply the number of links to the backup, the minimization of bandwidth consumption, and the minimization of read-write time. These three quality attributes are in conflict with each other, as increasing the number of links will also increase the bandwidth consumption and increase the read-write time, and then reducing the number of links will reduce the bandwidth consumption. The goal of our learner is to try and balance these three quality attributes without producing too much failure in the process. We have two possible actions to select, a minimum spanning tree, or MST, topology, or select a redundant topology, each with a cost or benefit for each quality attribute, summarized in this table in the bottom right. Our experimental results are as follows. The transition probabilities produced by our learner could perform similarly to those produced by an expert at a fraction of the time required. The learner could adapt to dynamic scenarios, achieving a range of behavior based on what scenario it found itself in. During our experimentation, we also found the need to calculate something called a PC value, which is a parameter representing the volatility in the environment. And confidence-corrected surprise turned out to be the most appropriate type of surprise for our purposes. Other ones we tested were Bayesian surprise and Bayes factor surprise. Our takeaway and contributions are as follows. We developed a novel approach for the learning of adaptation actions, We demonstrated the use of surprise as an indicator of broken assumptions during runtime. These have been tested for the use case of an RDM simulator, and a surprise-based learner will likely be appropriate in other scenarios, which we will eventually test. Thank you.